So hi everybody, I'm Josef Habdank and I'm lead data scientist and data platform architect at Infer, and I'll be presenting some really cool data science stuff that we did in our company and we're actually working continuously on. So before I go into what are we doing, Infer is a company that does analytics on airline prices of tickets, so that airlines themselves know how the market looks like. So for example, British Airways might be flying Copenhagen, Brussels, and then SAS might be flying there as well. So British Airways wants to know how SAS is pricing their prices so they can stay competitive. So that's what we do. We deliver this as a business intelligence product, and we're rolling out predictions on that. The really big thing that we are doing is, the really important thing from this slide is the sheer volume of data we're dealing with. People don't usually think that there's so many flights or so many pricing combinations that you can do, but currently we're doing 1.2 billion price observations every day, and they are unique, distinct prices. It's not like we're spamming. We're actually giving 1.2 billion different time series, distinct time series that we're looking at. And actually, that's not even the whole market. We're estimating the market to be in hundreds of billions in total, so that the number of prices is very, very large. This whole talk is divided into two sections. First, I'll talk about Ensemble approach for large-scale data science. And actually, I'm very happy about the previous talk because we're doing online learning as well. So I'm very happy to see that there are some improvements coming in the future version of Spark. And then the second idea that is there is you should think about the infrastructure. So first, I'll talk about theory, and then about practice, how you implement a very large-scale modeling infrastructure, what kind of technology you should use, and how you can structure your code so it works very well. So I have one slide about online learning. Those of you who have been on a previous presentation know already all this, so that's great. So there are two types of model training. You can do batch training, when you present the model the entire data, and then you crunch your data for 5 hours or 10 hours, and then you have your model and you're happy, right? The problem with this is that, first of all, if you think about it, if you're doing time series analysis and you want to do, for example, model on 1 year of data, in our case, that would be 400 billion rows. Even using Spark scalability to crunch 400 billion rows within 3-4 hours, it's a very, very difficult thing to do. But the other problem that is actually more subtle is that your model is being trained at midnight, for example, and then if some change in the market happens at 12 o'clock, your model will not know about this. So your coefficients will not be updated until the next day. And that is actually a problem, especially if you're dealing with very volatile signals. So the real thing what you want to do is you can, well, whenever it's possible, of course, you should try to do online learning in streaming fashion. So basically, the data would come into your system in batches. Let's say you have maybe billion rows a day, so maybe batches of 10 million, and then use these 10 million rows to update your models. And again, the really important thing here is that your model will always stay up to date. So that means if any change happens, 3-5 minutes later, the model is updated and you can and it's doing predictions better. And how the ensemble approach comes into play? Well, if you're doing with 1.2 billion different time series and all of them being separate, then there's no way you're going to have a single model that actually can cover all the corner cases of such a huge space. There will be such a vast differences in behavior, there's no way you can train one model for such a huge space. So what you should do, you should split your space into thousands or tens of thousands or maybe hundreds of thousands of subspaces, and then train single model for each of those groups, right? And then when you do prediction, okay, time series 5,000, that belongs to group 355, and then you get the model from this group and you do your prediction like this, right? So you basically break down a really big and difficult problem into thousands or tens of thousands of smaller problems which are manageable. So how you do this breakdown? So again, you're dealing with hundreds of billions. You have to be clever about it. So first thing that you do, you can usually have some knowledge about the data set, some business knowledge, that you can split your data into maybe 10 or 20 or 30 groups manually. But if you think about it, that's not enough. Because even if you make maybe 100 groups manually, which is already difficult, then if you're dealing with 1 billion, you still have 10 million groups, 10 million time series in each group. And that's still, 10 million time series, one model, that's not enough. You want to further split it down to have more granular space. So the second thing you would do is you would do clustering. So you take your created subgroups manually, and then you run cluster algorithm on that to maybe further split it down. So in the end, you maybe have 10,000 groups that you're going to train in parallel. The only caveat of this is that clustering methods are working only good if you have low dimensionality signals. So quite often you're dealing with thousands or tens of thousands or even millions of dimensions, and then clustering methods wouldn't work because the space would be very sparse. So you have to do dimensionality reduction. I'm not going to talk about how you can do it because you can have a 1-hour talk about just dimensionality reduction, but just remember you have to do it. Your optimal dimensionality would be maybe 7 to 10 dimensions for clustering. So I'm using right now Gaussian mixture model for this. It's my favorite, by far most favorite clustering method. And the reason why I like it so much is because it's fuzzy clustering, meaning it gives you an answer, not this particular time series belongs to this group, yes or no, but it gives you a probability, which actually is very useful if you do ensemble modeling in various cases, right? And the SparkML has a good implementation of it, which does the clustering in a scalable way, so it's very nice. On the left-hand side, you can see a chart which shows you some of the data that we have. Each point here is actually, of course, it's only 2 dimensions I'm showing, there's more. But each point here is actually entire time series, one entire time series of a price. So maybe a whole 1 year of data dimensionally reduced and shown here as a single point. Why this is important is just if you look at this data, you will see that different airlines, which are different colors, they lie on top of each other. There's a clear shape how the data looks like, and that means there is a lot of similarity between those time series, and grouping them would actually make sense. So let's look at the results of the Gaussian mixture. So I'm showing you 4 examples. One of the clusters here slightly up to the top. You can see it grouped a bunch of time series which are behaving very similarly. They're staying more or less flat, and then maybe between 10 to 5 days before the flight, the price starts going up. So you can see it grouped correctly prices which are similar, which is what we wanted. Then here in the middle, you have the main cluster, which is the central one, and you can see these prices are the kind of standard prices you would see, which is price of airline tickets slowly going up, maybe 30 days before departure going up over the days. Another interesting thing is that you can see it correctly have outlined outliers, because this is a very strange behavior for a price ticket. I mean, going up and down like this is very, very different than anything else, and it correctly have captured those as outliers, and here as well. The really important thing to take from this slide is that I haven't told the algorithm what I'm trying to achieve. I just told it, okay, here is my billions rows of data. Figure yourself out how can I group those so it makes sense. And it actually made very, very good groups for me. And if I trained models on those, you would see I would give it very different models, and it's much easier to actually do this because the model which is capable of predicting here is very different than the one from here. So that's a very good result and a very, very powerful, useful thing. Then I have one slide about feature selection and model selection. Again, this is a subject you can talk about for 3 hours, and I have 1 slide, so just a few pointers for you guys out there. So one-hot encoder, for those of you who don't know what it is, basically it's an encoder that converts some feature that has some groups, maybe three possible values, into a range of dimensions. And it does the work very well, because what you have is, for example, you have flight economy, business, and flex, right? So if you would use one-hot encoder on this, you would get 3 dimensions, which is not so much. But if you would use it on dimensions that have much more values, let's say 100,000, you would explode your dimensionality of model, and your model would collapse and not work. So basically, the lesson to learn, one-hot encoder is quite useful, but you quite often can do better than that. You should avoid actually using it if you can. What is much better is this one. What you can do is you can try assigning meaningful values to your labels. So for example, you have an hour dimension, right? Departure time of your flight, for example, right? And it has values from 0 to 23. Of course, if you plug this number into your model directly, the model wouldn't know what to do with it, because then the 23 doesn't mean anything to it, right? But you can actually look at the statistics of your data and derive values that you can translate your labels into some numbers, which are actually very meaningful for the model. So you can do that, and you can actually you can still stick to one dimension, but have actually very meaningful input. Another very interesting thing is try to use meta features. Meta features means that you have your data, and you can just take the values you have on a face value, or you can actually try to derive some additional stuff from it. For example, if you're doing prediction on a flight from Copenhagen to Brussels, you can just take the prices from the flight itself, but maybe additionally you can add an average of all the flights on this route from all the carriers. That will be a derived feature you can do, and that will actually make a lot of sense, and that can improve your prediction capabilities a lot. Another important thing is always think, how could you express a problem as classification, not always as a regression? Example of this is, again, prices. You could think, oh, it's a number, so it's a regression problem. But if you think about it, there are only maybe 5 prices that actually a ticket costs. Maybe a ticket costs $100, $200, $300, and maybe $500. So you have 5 groups, and you can actually take price prediction as a classification problem, and maybe it will give better results. I'm actually doing a lot of research right now into this. And then a bunch of libraries, right, which I like. If you do online learning, which I'll be showing in a moment, some code and some results from it. These two are very nice in Python. They allow you to do online updates on the model. And then there's a whole bunch of other ones. I even wrote my own library for particle predictor. There's a lot of cool stuff you can do with online learning out there. So before I go to actual implementation and how we did it, showing you some code, I want to show you the results to kind of prove that it actually works, what I'm talking about. So, so here on the top left side, on the top left side, you see a very interesting case of prediction. You can see I'm presenting only up till here to the model. So I'm presenting it a very uninteresting and boring part of the time series. It's very flat, and there's nothing interesting happening there. And because I do a lot of derived features, and I use the meta features and really thought about the process as a whole, I am actually able to predict fairly accurately 28 days, next 28 days of the price, which is actually a very good result. Another thing is this one. You might say, oh, the price is just flat, it's boring, but actually it's not. This is very difficult to achieve. Prices on airline tickets are an exponential process. So if you have an exponential process and you're modeling it, keeping model flat when it's supposed to stay flat is actually very difficult. It will always have a tendency to go up. So that's actually a very difficult thing to do, but because you, again, do really clever feature selection, and maybe there's a separate model for this type of behavior, and for this type of behavior, and for this type of behavior, then we're actually able to do that. And because all of those could land in different clusters, I might have different models for all these 3. So I'm able to do that. And then I have a bunch of different ones which are not so great, but still fairly okay. Okay, so now how we do this. So we know now we want to have thousands or tens of thousands of models. We want to train them. I want to use Python for this, Scikit Learn, because I want to use a vast amount of models that Python is giving us as a possibility. And I want to do it in an online way, so I can do it in a stream in Spark, right? How do we do that? So before you tackle a problem like this, you have to think of architecture. I mean, as a data scientist dealing with hundreds of billions of rows, actually, I would say 70% of your time, you'll be spending actually doing engineering, not data science. And that's just the way it is. If you have to do models on 300 billion rows, that's your primary concern will be performance and ability to scale, right? And that's an engineering problem. So I'm showing this just to show you what we did. So our data is being collected from the internet, of course, the prices, and then we send the data into Kinesis, which is the message broker, the same as Kafka. And we do it, we serialize it using Avro and compress it using Snappy, and then we insert it into Kinesis. And this is done in order to actually improve the performance. If you submit, let's say, JSON files, you will have maybe 10 or 20 times worse performance than if you actually do something more clever like this one with your data. And then we have a Spark streaming, which we actually host on DataBricks. And we build the data warehouse with all the data that we have. And simultaneously, right now, we're rolling out the predictions pipeline, which is still sitting in streaming. And it interacts with in-memory database, storing the minimum data that is required there. So both the models and some additional information that is required to do predictions. OK, so how is it actually done in practice? So this slide looks very similar to the one before, I mean, at the beginning of presentation, which is very good, because this is practice, and if practice is similar to theory, that's actually quite good. So what you have is, you have a stream of data coming in Spark, and Spark streaming basically works in such a way that you have it spawns batches of jobs. So if you collect throughout the entire day 1 billion rows of data, then maybe you will have every minute or every 5 minutes you'll have a 10 million batch that you work with, right? So the next thing you do is you group the data into clusters that you have pre-calculated before. So you sort the data out into clusters, and then you want to train one model per each cluster, and then update the model and store it back in database. So how can it be done in Python? So there's actually really clever tricks I did in order to make it work, and it works very, very, very nicely. The really important thing to remember is I want to train in a single Spark job tens of thousands of models simultaneously on the entire Spark cluster. So I don't want to have 10,000 small jobs that are running updates. I want to have one Spark job that updates all my models simultaneously using my entire Spark infrastructure. I mean my whole CPU power on the entire cluster. And that's the way it works. So first thing, if you think about it, you get 10 million rows like this, for example, in a single batch. And then you have, just some observations that you're looking at, some prices and whatever. And you can see a huge amount of rows belongs to the same cluster, obviously, right? What you can do is actually you can use a very powerful feature in Spark called collect list, which is a function for grouping. In normal SQL, if you do group by, you can get only single value, like minimum or max or average. In Spark, you can call collect list, and what it will do, it will group your data, let's say 10 million rows into 1,000 rows, but it will give you a column which is an array of all values within the row, right? So you're effectively not grouping data at all, you're just pivoting the table so that you have rows. Here you have only one row per cluster with all the data within the row, which is actually very useful. In the next slide you'll understand. But this is very powerful because normally in SQL you can't do this, but Spark allows you to do that. So what do we do next? So the most efficient way to interact between Spark and Python is to use UDFs. UDFs are really, really cool. Spark is very optimized to actually interact between Python engine and Spark engine if you are using UDFs. If you're using RDs, it will be awfully slow. If you're using UDFs, it will be much faster. So what you do is you're using UDF to train your model. The limitation of UDF is that you can only run your custom code, your custom Python code, on a single row of data. So if you had maybe 10,000 rows that you want to process in UDF, you can't do that. But because we have just collapsed all our data into a single row, the whole cluster of data, we collapsed it into a single row, now I can wrap my model training code inside a UDF, which will run on a single row, but that's what I want to do. Which can update my model. And as you can see, this is the data in and some model coefficients out, which I wanted to get. So before going into the code, how it's actually done, I wanted you to fully comprehend what is actually happening right now. Thanks to the UDF, which is doing the model training, we're parallelizing the model training on the entire cluster, right? Because the data will be sent around. Each row will end up in a different machine, and I'll be using all my CPU to train 1,000 on 10,000 models simultaneously. And that's what I wanted to achieve. I want to have one job that carries my entire modeling infrastructure forward. So, by the way, I'll post those slides on Twitter and LinkedIn, so don't have to take pictures. You can get those later. So this, as you can see here, it gets a single row of data, but these all features are actually arrays, right? So of course, this is feature 1 and 2 and 3 and so on, but all of them maybe have 1,000 elements. It's an array of values, right? So you effectively have a matrix. This whole parameter set here is actually a matrix with 7 columns, right? So what I do here is basically I convert it into a more Scikit Learn compatible format, and then I'm getting my where is it? I'm normalizing the data, then I'm getting the latest version of the model, which was saved in the previous streaming batch. I'm getting it into my function. Then I'm doing partial fit using the data in a matrix format, which I created here from all those inputs. So I'm making my partial fit, which means I use online learning on this model, and then I convert it into a Spark compatible format so I can return it from the function, right? So effectively here, I have got my matrix of 1 million rows or 10,000 rows, and I get my model, update my model, and I return it back to Spark. And again, there will be 10,000 of those running, and I'll be pushing my whole modeling infrastructure forward. So how do you actually do prediction as a service afterwards? It's actually very, very straightforward. At this moment, you have everything that you need to do prediction as a service. So you have all the models inside the database, maybe in-memory database. You have to have some additional data, maybe in some other database to do predictions, especially if you do time series. But you have to have both anyway to do model training. So now you have a nice infrastructure that allows you to do predictions. And what you do is, when the request comes for prediction, you find the cluster that this time series belongs to, you grab the model, you grab the necessary data that is required to do prediction, you do your predictions, and you return them from web service. A little trick that most likely most of you know, but I'm going to still say this, is that if you do time series models as a regression, you can formulate a time series problem as a regression. Well, actually, no. Pretty much always it does it. So if you do time series prediction, you basically make prediction 1 day ahead. So if you have maybe 50 days and some additional features as your feature vector, you do one day prediction. But if you want to have a result of 20 days prediction, then you shift your window. You just made a prediction. You shift your window one step forward, and again you make +1 prediction. You shift the window again, and you continue on like this. That's a small technical implementation thing. A very important thing from this is that actually you don't have to work with the same model. Because you're doing with 10,000 models or 100,000 of models, and all of them are uniquely associated with a certain subspace, right? Nothing limits you to actually have the same model for all the groups that you're dealing with, right? You can actually have classifier model for this one and maybe linear regression for this one, SVM here and particle predictor there. You can actually custom tailor your models that you want to have for the specific case. Because if you remember from the Gaussian mixture slide, the behavior is very, very different. So it does make sense to have maybe more models, not just one type, for each group. And again, the workflow would be the same. Your whole infrastructure would look the same. Your streaming job would look more or less the same, because, well, that's it. You have distinct models. There's nothing preventing you from using different ones. So that's it. I'm actually ahead of time, so that's good. I can take some questions. But so a few short summary. So Spark in Python is awesome. Because it comes with an enormous capabilities from Python. Python for machine learning is amazing, and if you can combine it very well, and this is how you can combine it, if you can combine it with Spark, which enables you to do it in a very scalable way, it will give you a very, very good results and a very short time to deliver your product. You can do very quick iterations on your work. Second thing, always get your infrastructure right. I mean, I cannot emphasize it enough. You can't do a very large machine learning on hundreds of billions of rows without the right infrastructure. You have to have message broker like Kinesis or Kafka. You have to have Spark streaming. You have to have some in-memory database. I mean, we have heard by so many speakers, I'm using Redis, I'm using this, I'm using that. A lot of companies are using in-memory databases. We shouldn't be afraid of that. Use notebooks for your development. They're amazing. DataBricks has a very good one, but there are other ones if you don't want to use DataBricks, even though I recommend it actually. There are other companies that deliver notebooks experience as well. Another thing is always when you have a big problem, and in big data you usually have big problems, try to break it down from one unmanageable, gigantic thing that you want to solve into thousands or tens at least of smaller problems that will be much easier to solve. And Ensemble Learning helps you with this. Gaussian mixture, my personal favorite, maybe not yours, but I always recommend it. It works very, very good. And the fuzziness is a very important aspect. And then lastly, and I think very importantly, or maybe most importantly, use in Spark, use always DataFrames and use UDFs. You will have either tens or even hundredfold faster performance compared to RDD if you use Python. So pretty much, I don't even look at RDDs anymore. I always use UDFs. So just before I leave, we are hiring. If you're a data scientist, we're doing really cool projects in data science. If you're a just big data engineer, come as well. We're really cool. We're working with cool technologies, and problems are very interesting. Come and work for us. We'll welcome you. So that's it, and I have time 4 minutes for some questions. Thank you. Thank you.
Questions? Okay, start here.
Hi, you mentioned you were clustering time series. What are you using as a measure between those time series?
Sorry?
You're clustering time series, right?
Yes.
Which means you have a distance between the time series considered as point.
Yes, yes.
What is the distance?
Yeah, well, you have to dimensionally reduce your data, right? And then you can just use either Cartesian or... I mean, I think that it's not about the measure. The measure is less important. I think how you dimensionally reduce the data is actually much more important. If you think of time series as a 1 point, right? So you have maybe 1 year of data, which is 365 points. That's 365 dimensions. It's more important that you reduce dimensionality than focus on metrics.
But what are you using for dimensionality reduction? Something like PCA? You'll get...
No, we use... Let's talk after the talk. It's a very interesting trick I did, but it's quite complicated. I don't want to confuse everybody.
Okay.
Yeah, come to me later.
Yeah, thanks for nice presentation. I missed actually the point where you apply the Python code, like on a Spark worker, right?
Yes.
How do you optimize it actually working only on some partition of your whole data for one model? If I understand correct, like the data for one of thousands model, it would be distributed like along multiple workers.
No, it won't because of this trick, right? Spark cannot send a single row to 2 workers. Single row will always end up in a single machine. So what I'm doing here, I'm collapsing my observations such that there is always 1 row per cluster, and that this row contains all the information that it needs as an array. So that means I have a huge, maybe couple of megabytes of data inside the 1 row, but then I'm guaranteed that this 1 row will end up on 1 worker, and then I have the entire data to run my model update on single machine. So this trick does what you're asking for.
Okay, and the second question is about clustering. Did you try some kind of simple methods like feeding some mean, median, minimum, maximum, and standard deviation to cluster those time series?
That would be, I mean, that could be part of your pre-processing. We do dimensionality reduction, which is a little bit complex, but you can add those into your features to help the clustering. Yes, as additional features, right? So I would not maybe use those to cluster only, but I could add them as additional features so that clustering can utilize those extra information.
Thanks.
Yeah.
Great talk. I have a question regarding the some other inputs other than the new data points that come in. I mean, you have each 10 minutes new pricing, new flight pricing data, but also for your classifiers, for instance, they have false positives, maybe.
They have, sorry, what?
Some errors,
Yes.
some misclassification. How do you make the models learn from the mistakes that they make?
Yeah, well, that's a very good question. So basically, in production, you would want to maybe have single model that is being used at the time, maybe a couple, maximum 2 or 3 per each cluster, not maybe too many of them. So one thing to shield is, since you're already training thousands of models, maybe you can train tens of thousands and you can train 3 per each group. per each, right, three models with a bit different parameters, and then you can, in real time, basically figure out which one is making more mistakes, and you can adapt in that way. Because it's a streaming fashion, it's very hard to kind of make oh, now I review everything, because it's long gone whatever was happening before. So the only thing is kind of make some sort of A/B testing or adaptive adaptive weighing of models if you have multiple of them, right? But I agree, it's a tricky thing to handle, yeah.
Okay, thanks.
I think time for just one more question, maybe. Anyone at the back? To have a go? Yes, one there.
Hi. Thanks for the presentation. Can you explain a bit more how you converted the feature for the RO223 to probability or to...
Yeah, I can see you, but I can hear you, so that's okay. Yeah, so it's actually fairly straightforward. There's no philosophy in this. You basically look at your group of data, and you make simple statistics. So you group by the hour, right? And then you look at the prices, and then from the prices that you just grouped by and maybe did some normalization on, that will be your value here. So it's actually very simple statistics that you can do. And the good thing is that you can actually, if you're clever, you can do this in streaming fashion as well. You can keep updating those values in a streaming fashion as well. So we didn't do anything clever. You can do actually much better than that. But it works very well, so that's what we did.
Okay, that's great. So show our appreciation for Joseph. Thank you very much.
Thank you very much.